Today is going to be kind of a later day, good day to end the week on. And we're going to look at one additional method for integration, and it's used when you have rational functions. And I mean, we can use substitution if the numerator is a constant multiple of the denominator. That's fine. However, if they're not constant multiples, then we need another method to deal with this, and integration by parts really wouldn't work. So we have this thing called partial fractions. And partial fractions are the simplest fractions that when you combine them, you add them or you subtract them, they give you a rational function. So we're going to start with the rational function and find the fractions that have been combined to give you that function. You know, like 3/4, we could break that apart, and that could become 1/2 plus 1/4, and that would be kind of the idea with partial fractions. So we'll see something like this. And again, the first thing, if I saw a problem like this, the first thing I would do is think about substitution. You know, if u is my denominator, and then my derivative, and now can I multiply 2x plus 1 by something to get 8x plus 1? I'm going to say no. So substitution isn't going to work. So here's what we do with partial fractions. The first thing we're going to do is factor the denominator. And if we factor the denominator, I believe this denominator factors into x plus 2 times x minus 1. We can just double check real quick. X times x is x squared. 2x minus 1x is 1x. 2 times -1, -2. I like it. So 8x plus 1 over x plus 2, x minus 1 has to be some combination of a over x plus 2 plus b over x minus 1. So what we're doing is the numerator of our fraction on the right-hand side is always going to be 1 degree less than the denominator. So this is a linear denominator. The numerator is going to be a constant. On the AP exam, your denominators will always be unique linear terms, because there are other strange things you have to consider if they're not. So it would always be something like this. You might be given the denominator already factored, although usually it's not. So, you know, brush up on your factoring if you need to. All right. Then what I would do is multiply by this denominator that I have on the left-hand side. So I get rid of my denominators. When I multiply it by it on the right for the first term, the x plus 2 cancels, leaving me with x minus 1 times a. And for my second term, the x minus 1 cancels, leaving me with b times x plus 2. Go ahead and multiply out the right-hand side. And now what we're going to do is break apart this single equation to make two equations. So I know this 8a, I have to be able to get that by combining ax and bx. So 8x has to be equal to ax plus bx. And then my constant term 1, I have to be able to get by taking negative a plus 2b. The last thing I'm going to do on the this top equation, I'm going to divide everything by x. So if I divide everything by x, I get 8 equals a plus b. And my second equation, 1 equals the opposite of a plus 2b. And now I can solve for either a or b by using things like substitution or elimination. I could use matrix manipulation if I wanted. In this case, I think it's pretty easy to just add the two equations together. And then we get a plus negative a, that's 0. B plus 2b is 3b. Divide by 3, and I get b equals 3. Using my system, I can solve for a by plugging into either equation. It might be just easiest to plug into the first one. All right, so what that means is 8x plus 1 now I want to make sure I get the numerators right. A is going to be over x plus 2. So 5 over x plus 2. And 3 goes over x minus 1. Now, if you're unsure if that's really true, go ahead, find your common denominators on the right-hand side, and then combine your numerators. I think you'll be pleasantly surprised that that is true. What this means for our problem is now, instead of this integral, I have this integral, or this pair of integrals. And these integrals I can deal with. And actually, I can deal with them pretty easily. The 5 is a constant, if I have, excuse me, if I have a constant over this x plus 2, you could think about substitution, although if there's no coefficient in front of the x plus 2, we're just going to get an ln. Same thing here. We've got that constant 3 out front. We're going to get the ln of x minus 1. We're going to add a constant to it. Usually we're not going to stop there. More than likely, we will want this to be written as a single natural log. So we're going to use our laws of logarithms and kind of use them backward. Normally we do things like take a power and bring it out front as a constant. Well, here we're going to do exactly the opposite. I'm going to take our constant that's out front and make it a power. And then we can write this without the addition. The addition of two logarithms just means that you are multiplying whatever it is you're taking the logarithm of. And this would be then our final answer. So if you really want to check your work, take this original expression, take its derivative, and see if you get that 8x plus 1 over x plus 2, x minus 1. And again, I know a lot of fun. I'll leave that fun for you to do if you're not sure that you can trust Mr. Gingrich. All right, so here we have one that's already factored. So that's nice, a little less work. And I think it's standard convention to use A and B. If we had a third factor, we'd have a plus C over whatever that third factor is, and so on. Multiply to get rid of my denominators. Distribute. Now write our expression, and I'm actually going to not write the x's. So this 1x would be a plus 3b, and 18 would have to equal 4a plus 5b. So again, you could use either substitution or elimination. I'll be honest, for these, I normally use elimination. So I would multiply this top equation by -4. and then add. The a's cancel. Dividing both sides by -7, I think I get b equals -2. Plugging that into one of my two original equations here, maybe 1 equals a plus 3 times -2. And now I can rewrite my original integral as the integral of 7 over 3x plus 5 minus 2 over x plus 4. And again, if you would rather write that as plus -2, you can. No problem there. This one adds a little bit of a challenge with the 3x plus 5. So I'm going to show it using substitution. And then there's going to be, I hope, kind of an aha moment. So if I let u equal 3x plus 5, then du would equal 3 dx, or 1/3 du equals dx. So I have that 7. I'm going to pull that out. With my substitution, I get a 1/3, 1 over u du. Again, I can pull the constant out here. Seven thirds. Integral of 1 over u is the ln of u. I could use substitution on this one as well, just calling it a different variable. If you'd like, I can certainly do that. I don't want to use v. W could equal x plus 4, then dw would equal dx. So I get ln absolute value of w. Substitute back in for u and w. So here's what I hope that kind of aha moment would be. When we have a number in front of the x, a coefficient with the x, it becomes the same value in the denominator of the integral. Now to write this as a single natural log, First, we bring the constants in, put them as powers, and we can write or rewrite subtraction as division. These problems, I've seen them almost exclusively. Can't remember a free response question where I've seen them. They've always been in the multiple choice section. Now, of course, I say that now, and guess what's going to happen on your exam this year? Oh, you're going to have partial fractions on the multiple choice section. All right, one more example. Factor my denominator. Rewrite it as the sum of two fractions, one with a over one factor, the other with b over the other factor. Again, it doesn't matter which order you put them in. The signs work themselves out. So if you wanted to put x plus 1 first, you could. Multiply by that denominator. Distribute. Rewrite. 5 has to be a plus 2b because those are the coefficients with my x's. Negative 4 has to be a minus b. Those are the coefficients of my constant terms. Again, using substitution or elimination, or I just like elimination for these because they're usually pretty straightforward. Might be a little more difficult if you have coefficients on both of the x terms. But if I take that second expression and multiply by negative 1, or I could just subtract. I get b equals 3. Plugging that in, 5 equals a plus 2 times 3. 5 equals a plus 6. Negative 1 equals a. So 5x minus 4, 2x minus 1, x plus 1, negative 1 over 2x minus 1, And I would always write these as separate integrals. You could write them as the same integral. It doesn't matter. I just am more comfortable writing them as two separate integrals. Using our AHA from the previous example, I am going to get a 1/2. I'm also going to pull that negative out front. And again, if you're not yet at that point where that aha moment makes sense, you can certainly use substitution. I've only been doing this a few years, so, you know, like 30. I'm going to pull the 1/2 inside. And now this one's a little bit different because the first term is negative. So that just means in my logarithm, the 2x minus 1 to the 1/2 goes in the denominator, and the x plus 1 cubed goes in the numerator. Questions? No, Mr. Gingrich, this seems like a lot of fun. Can we do some on our own? Certainly. So you'll see there are 4 problems on the assignment. Just a nice little bit to practice on. I also thought this would be nice to give a short assignment just in case you need to work on any of the substitution or integration by parts stuff, which is a little bit more of a heavy topic compared to partial fractions, I think.